Hi, my name is Rachel. I'm a postdoc at the Neural Computation and Cognition Lab run by Professor Michael Frank. And here's a brief summary of my study. So the aim of this study was to specify the decision parameters involved in cognitive control of working memory and the time-sensitive neural correlates. Effective cognitive control depends on a hierarchical gating network which regulates motor and cognitive action selection, including working memory updating. The gating network is composed of several circuits that thought to mostly operate in parallel. So the higher level gate is the input gate, which gates working memory information like task set into the PFC, and it contextualizes gating decisions at the lower level. The mid-level, the output gate, is making the selection from within working memory, selects the context to guide the response selection. And finally, the lower level circuit is the response gate, which selects the response that is appropriate given the context provided by the output gate. A very important feature of this network is that there is a gate switch in each of these levels. So a switch is when a representation needs to be selected by the gate that is different from the representation selected in the previous trial. So that kind of switching requires a switch cost. And another very important feature of this network is this diagonal projection from the medial PFC to the SDN. This pathway acts as a temporary break over the response gate. It is triggered by conflict at the higher level, frontal representation. Computationally, what this means is that the decision threshold is raised over the response gate, allowing the response selection to be delayed until cognitive uncertainty is resolved. Evidence for this threshold adjustment dynamic was never shown within a working memory paradigm. The prediction is that the selection of information within working memory also involves a cognitive conflict that will be expressed by threshold adjustment. Using a variant of the reference back task, which is a working memory updating task, we were able to directly manipulate each of the gating levels independently. The behavior results showed under-additive interactions between all the different levels of this network, supporting the idea of parallel processing. The univariate pattern found in the EEG also demonstrates mostly parallel processing, as you can see. Using a type of decoding approach, we were able to obtain a trial-by-trial measure of the gating-related activity at each level. Using the drift diffusion model of decision-making, we aim to test if trial-level change in the model parameters, threshold and drift rate, could be predicted by trial-by-trial variation in the gating activity. What we found was that the trial-by-trial increase in response gate activity was related to an increase in decision thresholds. So this is specifically what you can see in these orange bars. So the neural activity of the response switch gate led to an increase in threshold, but this was specific to conditions where the higher level output gate was not active. However, when the higher level output gate did switch, and then we no further see any increase in the threshold during response gating. This is explained by cognitive conflict caused by the gate switch at the output level. The output gate conflict triggers the increase in the threshold on the response gate through this diagonal pathway, overriding the response gate effect. This results demonstrates the top-down influence that working memory control can have over the response gate. Thank you for listening to this brief summary. I'm very happy to chat and answer questions or just brainstorm over these results. Thank you.